In the previous video, we defined union, intersection, complement, and difference of sets using logical notation. We're now going to prove some identities connecting those operations, making use of all the things we learned in Chapter 1 about logic. So let's begin with a very simple property of unions and intersections, which is a really natural one and a very clear one if you think about the definitions. It says that if you have two sets, A and B, then A intersect B is equal to B intersect A. That's the first part, just here. And the second part says that A union B is equal to B union A. So let's think about how we would actually write a proof of one of those things, because although these are quite obvious properties, the way we prove it will be used as a template for how we do all the other proofs of set identities. And the way we're going to do it is by thinking about logical equivalences. So I'm going to remind you of what is Theorem 1.5.1 in the notes. And part of 1.5.1 says that if you have the well-formed formula P and Q, that is logically equivalent to Q and P. And you'll remember that logical equivalence means that those two formulas are true under exactly the same truth assignments. So one of them is true if and only if the other one is true. Let's think about the first part of this theorem then, to do with intersections. So you'll recall that A intersect B, or A meet B, is equal to the set of all things X, such that X is in A and X is in B. Okay, now you can see where the connection with logical equivalences is going to come in. So we have, because of this logical equivalence, that X in A and X in B is true if and only if X in B and X in A is true. And that's because of this logical equivalence. So by 1.5.1, that's the theorem in which we proved the result of which that logical equivalence is a special case. So what do we have? Well, this thing here is the condition for a thing X to be in A intersect B. And on the other hand, this here is the condition for a thing X to be in B intersect A. So X is in A intersect B. This is for any thing X if and only if X is in B intersect A. But that is the definition of two sets being equal. Two sets are being equal if something is an element of one, if and only if it's an element of the other. So A intersect B equals B intersect A. Alright, and we can prove the second part of Theorem 2.31 in the same way. That time we need the logical equivalence that P or Q is logically equivalent to Q or P. And again, that's part of Theorem 1.5.1. Okay, so that's the commutativity result for unions and intersections. And there is similarly a associativity result. And this time I'm not even going to bother to write the proof down. All I will say is that this results from a logical equivalence. So this follows in the same way from, in fact, the same theorem. So 1.5.1, where it's shown that if we have P and Q and R, then that is logically equivalent to P and Q and R. So we can use that logical equivalence to prove that A intersect B intersect C is equal to A intersect B intersect C. And similarly, the same thing for OR can be used to prove the second part of this theorem. So the equivalence for OR, the associativity result for OR is that P or Q or R is logically equivalent to P or Q or R, like this. So we get the same result. And also for distributivity, we proved distributivity properties for and OR. So this was Theorem 1.6.1. And in 1.6.1, one of the results that we proved was that P or Q and R is logically equivalent to P or Q and P or R. Now that proves part 1 of this theorem, because if you unwind the definitions of those sets, A union B intersect C would be the set of all things X with the property that X is in A, or X is in B and X is in C. But this formula here is logically equivalent to saying that X is in A or X is in B and X is in A or X is in C. That's the logical equivalence of theorem 1.6.1, the distributivity theorem for or and of course what I've written there is exactly A union B intersect A union C. Okay, so these logical equivalences gives us all kinds of useful results connecting the main operations in set theory. But in this video we've only seen identities involving union and intersection. So in the next video we're going to start taking a look at the other set operations.